So the third course of the program. So you had the first lectures in 2 courses this morning. So the third one I start. If I haven't met you, my name is Surya Ramana, and I'm doing this course along with Gyan Prakash, who's there. And this is on the famous Green-Tao Theorem. I'll be telling you what it is. So our aim is to give an overview, try to get as close to a detailed proof as we can in the limited time that we have, at least the details that we think are the important ones, and then probably leave out a little bit either because it's too difficult to cover in 2 weeks, or because we think that the person who knows much of what we do can read the rest herself or himself. Okay, so first, the Green-Tao theorem deals with arithmetic progressions. So just to set notation, a k-term arithmetic progression is a plus d, a plus k minus 1d, where mostly a is a natural number. These are all natural numbers, and k is also n. So this is greater than k is usually greater than 1. In fact, normally k is greater than or equal to 3. So we are at least, I mean, to consider non-trivial APs, you need at least 3 terms. And this is what I mean when I speak of an arithmetic progression. Okay, so of course everybody knows this definition. It's simply to make sure that there is no confusion later. Okay, so I mean, it's not usual for someone to just define an arithmetic progression and immediately state the Green-Tao theorem, but that's exactly what I'm going to do. So first of all, for a set, so if when A is a subset of P, which is the set of prime numbers, we write an to be the number of elements of A which don't exceed n. So it's this number, and one speaks of the relative upper density of an. So the relative upper density of an is limit supremum of an by pi of n tending to plus infinity. This is called the relative upper density of A in P, where here pi n is of course the standard arithmetical function, which is the number of prime numbers up to P in P less than or equal to n. Of course, this notion is very familiar to most students here, except maybe not in the relative situation, but when A is a subset of the natural numbers. So when A is a subset of n itself, considered only as a subset of n, then the density, upper density of A is the limit supremum n tending to infinity of an, this time by the total number of natural numbers up to n, that is this. Just to recall that this is the notion of upper density, it's the limit supremum of this, and the relative upper density when A is a subset of the primes is this limit. Okay, so the theorem tells you, that this theorem of Green and Tao says that if when A is if A is a subset of P with relative upper density of A strictly positive, so greater than 0, then for each integer k greater than or equal to 3, A contains an arithmetic progression of k terms. Okay, so it tells you that if you take a subset of the primes which has relative upper density here, the quantity I just defined, this quantity, if this is strictly not equal to 0, it's always greater than or equal to 0. If it is not equal to 0, then A contains arbitrarily long arithmetic progression. Arbitrary long means, of course, finite APs of any length it would contain. Okay, this is a remarkable theorem. Of course, it was a long, it was sought after for a long time. It's a remarkable result, mainly because, of course, it's a hard theorem to prove. Plus, this is one of those things that talks about additive properties of multiplicative subsets. And typically, when one mixes addition and multiplication, one gets hard problems. So this talks about an additive structure, namely having an arithmetic progression inside a multiplicatively defined set, namely the set of prime numbers, which are the basic multiplicative subset of the natural numbers. You know that there are similar problems, similar as in within this, there are other famous problems falling within this theme like Goldbach conjecture or twin primes and so on. So this is a problem of a similar sort, and it was quite it was open for a long time, and it was a spectacular achievement when this was proved. At least the paper is in 2008. They probably proved it earlier. I do not know the exact time when it was proved. Okay. Now, before Green and, so this is Ben Green and Terence Tao. Before Ben Green and Terence Tao proved this result, Green studied and proved the 3 AP version of this. So arithmetic progressions in 3 terms are a especially interesting case because they are much simpler than k-term, analyzing k-term arithmetic progressions. Of course, a 3-term arithmetic progression by this definition is simply A plus D, A plus 2D. But there is another way of saying that 3 numbers are in arithmetic progression, and that is by saying that, so to say that 3 numbers are in arithmetic progression, a better way to say it is to say that x, if x, y, z are in AP, a better way to say this is to say that x plus z by 2 is equal to y, or even still better, x plus z is 2y, or even better is x minus 2y plus z is 0. Okay. Now all these things can seem like trivial translations from one to the other, but actually they give you different points of view. So here to say that you have a 3-term AP, if you look at this particular equation here, the left hand side, the sum of the coefficients is 0. Okay? So if you have any solution x, y, z belonging x, y, z to this equation, then x plus h, y plus h, z plus h is also automatically a solution, because any translate of a solution is a solution to this equation. Okay? So such equations where the sum of the coefficients is 0 are called translation invariant equations. And much of what I say will apply to translation invariant equations in any single translation invariant equation in any number of variables. So the methods I use and the theorems I give, you can easily extend them to a single translation invariant equation in any number of variables. Okay? So it's this point of view that really governs how one studies 3-term APs. The fact that x, y, z are in AP is equivalent to saying that x, y, z satisfy this particular equation. So with 3-term APs, it turns out that studying a single translation invariant equation is probably the easiest case in this sort of a theorem, and therefore it's not very surprising that the first result was actually proved by Green alone in 2005. It was published in 2005. Again, I do not know when it was proved. So what did Green prove? Green proved, yep. Yeah, and okay, I must be very careful here, and thanks for pointing out. All of this question, I mean whether the AP of k terms or 3 terms is interesting only if the AP is non-trivial. Okay, so a trivial 3-term arithmetic progression would an arithmetic progression in 3 terms is trivial, of course, if x is equal to y is equal to z. This is the trivial. Okay, this is because this is always a solution, and you take any subset of the natural numbers, there will be a triplet like this with all 3 variables belonging to that set, because they are all equal, you can just take any element. Okay, so these are the trivial solutions to this equation, and we are of course constantly interested in the existence of non-trivial solutions in certain sets like the primes. Okay, so when I say k-term arithmetic progression, I of course mean that the k terms are not all the same. I mean, then there is no this is no big deal. Okay, so having said that, here is Green's theorem. So the theorem of Green so this is 2005 if I remember correctly, is that if A is a subset of 1 to n of the primes in 1 to n, so A is a subset of P intersection 1 to n, and A does not contain non-trivial 3-term AP, then the cardinality of A must be small is less than or equal to some constant. So I will use the notation that analytic number theorists use. Less than meaning there is a fixed constant here which I don't mention. Okay, square root of here is another notation. Okay, I'll probably not use the notation, but I have to be careful to write the correct number. Yeah. So this is log, say you can write 5 n. This is log 4. Okay. So there is almost sounds like an old joke goes, sounds like a drowning man, log, 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 log. Okay, so there are 5 logs on the numerator with a square root and 4 logs in the denominator. This is the original result. It has been improved subsequently. In fact, we will follow a method which led to one such improvement, that's due to Helfgott and Ronthon, which came much later. So, I mean, few years later. Pardon? No, here it is, yeah, pi n. N by log n should be here and then 4 by 4. Pardon? Oh, base is always only one base, which is the natural logarithm. When I write log, I mean actually ln of n, if that's the notation you use. Okay? So this is the result. As Shatadil pointed out, this should be pi n, and change it from n to pi n, and otherwise you should write n by log n here and remove the denominator from there. Okay, so you see that if it does not contain 3-term arithmetic progression, its size is practically equal to that of pi n. It's just by a tiny sliver it falls below that. Okay, this root of 5 logs by 4 logs is like a small quantity, but of course enough to say that A must have 0 density as n increases. Okay, so it follows from this, of course, that if n is large enough and A is greater than delta n, so it's a positive, it contains a positive proportion of the primes, I mean delta pi n, then A will contain non-trivial 3-term arithmetic progressions. Okay, because a set of positive density does not satisfy this inequality, because this is a quantity which is going to 0 with n, even if it's going to 0 very, very, very slowly. Okay, log n is almost a constant. Now 5 logs and 4 logs is practically constant, but nevertheless it goes to 0 with n, and that's the result. Okay, so here it's stated in this form rather than positive upper density, but this immediately implies that if A is a subset of the primes having relative upper density positive, then in fact it contains infinitely many 3-term arithmetic progressions. Because once a subset has positive relative upper density in the primes, then you see there are infinitely many n for which the intersection of A with the primes up to n is greater than delta times n. I mean, if the upper density is say delta, then there are infinitely many n for which the cardinality of A by the number of primes is greater than delta by 2. Okay, and so if you apply this theorem to that situation for those infinitely many n, you see that each of those A's contains 3-term AP, and that at least proves for you that the set A contains 3-term APs, non-trivial 3-term APs, and since the relative upper density doesn't change if you throw out finitely many elements from the set, you actually get infinitely many 3-term arithmetic progressions. Okay, so I could state this result like Green-Tao's theorem, but I have stated it like this because Green actually proved a stronger statement, which was this. So this implies Green-Tao for k equal to 3. Okay, this implies Green-Tao for k equal to 3, and the justification is just as I said, it's a small consequence of the definition of the notion of relative upper density. Okay, now this is all about subsets of the primes, but historically this was the harder problem, because the much easier looking problem, I don't say much easier problem, the much easier looking problem, which is if A is a subset of 1 to n, okay, then and does not have a 3-term arithmetic progression, then is it true that A must be small? Forget about being a subset of the primes up to n. Primes themselves are a sparse subset of the integers up to n. Let's just consider a subset A of the integers up to n, and if that didn't have 3-term APs, non-trivial 3-term APs, then the question is it true that the cardinality of A is small? Okay, that was actually the original question that motivated these things, or a similar one, the Erdos-Durand conjecture for not just 3-term arithmetic progressions but k-term progressions, and for k equal to 3, Roth settled this question in 1953, starting a whole branch of activity within combinatorics and analytic number theory. So I should first state the theorem of Roth. And the reason for stating the theorem of Roth is not just to get the history in order, but it's because the proof of Green's theorem that we will give will actually go reduce to Roth's theorem. Okay, the idea is to somehow reduce to Roth's theorem. So here is theorem of Roth from I think 1953, perhaps 1953, which is that if A is a subset of 1 to n and A does not contain non-trivial three-term APs, then the cardinality of A by n is less than 1 over double of n. Okay, so here too the cardinality just slips from n by a small 1 over log n. Okay, so this it follows from this, I can write this statement in another equivalent fashion, and that is so equivalent version would be, so equivalent statement theorem is if delta is positive and then for any n greater than exponential constant by delta, and any A subset of 1 to n with cardinality of A greater than delta n, then for any there is a non-trivial 3-term AP in A. Okay, so this is C is just a constant. Like here, this implied constant, there's just no notation, similar notation when you double exponentiate. So you have to put a C. Okay, here the notation allows you to, take in the C into it, but there's no corresponding notation. Okay, so here C is some constant. So what this says is that if A is having more than a positive proportion of the number of the integers from 1 to n, then A automatically contains a non-trivial 3-term AP. If you fix the proportion, you have to go far enough for the n. It has to be bigger than something like this. But once you do that, any set which contains more than a proportion, that given proportion of the numbers from 1 to n automatically contains a non-trivial 3-term AP. Okay, this exponential constant by delta simply comes out of putting delta here and inverting the relation between n and delta. So you will get constant by delta and double exponential for the double log that is there here. Okay, so this is just, you could similarly write a version of Green's theorem, except that the dependence on delta is going to be somewhat ugly. Okay. I don't know about explicit results on Roth's theorem. Okay, I do not know. So this is Roth's theorem, the equivalent version. So now let me tell you what is the plan for the course, since I have told you the main results at least. So my plan is to prove Green's theorem. Okay, I will do that by first proving Roth's theorem and then reducing Green's theorem to Roth's theorem. Once I am done with it, Gyan will lecture on the proof of Green-Tao itself, where a similar strategy, after all they actually built on the strategy of Green. Okay, so a similar strategy will be used, but of course there's a lot more to be done. But roughly speaking, there's the template is very similar. Okay, so that's how we'll present the material. But the problem, the point will be that now we have benefited a lot from hindsight. So the proof of Roth's theorem I'll give is not at all the original proof. It's a proof based on Green's theorem. So inspired by Green's theorem, Kroot and Sisask came up with, Olaf Sisask and Kroot came up with a proof after Green's theorem of Roth's theorem. So we'll give that proof. That will already contain the elements of how Green's theorem works. And then we'll go to Green's theorem, which will follow that method or that principle and finally reduce to Roth's theorem. Okay, so we'll build the same strategy first by proving Roth's theorem, then by proving Green's theorem, and eventually outline the Green-Tao theorem by adding in a lot more, but following similar ideas. Okay, so now before I launch off into Roth's theorem itself, let me tell you that it's interesting to note a result of Behrend, which came before Roth in 1946, which in fact went the other way. So it showed the existence of sets with fairly large cardinality, I'll write down the exact thing, which do not have 3-term arithmetic progressions. Okay, so we'll see Behrend's construction, which is very simple but ingenious. I mean, it's almost the natural way of constructing sets without 3-term arithmetic progressions, and we will see the lower bound given by Behrend. We will note that the upper bound given by Roth is far away from the lower bound given by Behrend, and even the best result known on Roth's theorem at this point, which is here, if you replace this by, I think, log n to the power of 4 divided by log n, This is very recent, maybe last year or so, by Thomas Bloom and Olaf Sisask, if I'm not mistaken. It's about last year. So you see this result, even this result will be far off from the only known examples that we have for sets that don't contain 3-term APs. Okay, so what is Behrend's theorem? So here, last year, I think it's 2018. This result is probably 2018, not 19. Or maybe in May of 2019, something like that. It's very recent. So, theorem of Behrend from 1946. So, you should note that this theorem is before Roth's theorem. So there is a subset A of 1 to n with cardinality A greater than A by n greater than exponential some constant times root log n, such that A contains or A does not contain any non-trivial 3-term AP. Okay, so for all n large enough, you have subsets whose size is exponential minus constant root log. Now you know from the exponential series that this is less than 1 by logarithm n to the power of anything. So the sets you are able to construct go all the way here, not just log n, not just log n, but log n to the power of anything you want. Okay, so those are the only examples we have. Whereas the theorems we are able to prove are far away from the examples we have. Okay, so this is basically there's been only very little done above what Behrend originally did on this thing, and even that very little is non-trivial and ingenious, but I won't go into that. I just want to tell you the proof of Behrend's theorem because that shows you a natural example of sets without 3-term APs. And it also tells you why it's important to consider 3-term APs as actually solutions to the equation x plus y x plus z equal 2y. Okay, so the equation x plus z equal 2y, you see, makes sense even in a vector space. So in Rn, it makes sense in Rn, right? So you can find points in Rn which are, you can speak of solutions to this equation in Rn. Now there are natural sets which do not contain solutions to this equation in Rn. Okay, those are extreme points of convex sets. Of course, we will be interested in the simplest case alone, namely spheres. So you think of a sphere in Rn and think of the boundary points. Every boundary point of a sphere in Rn is an extreme point. What does extreme point mean? You take any 2 points, then if you have a third one, which is the midpoint of the line joining these two, namely if y satisfies x plus z by 2, then necessarily y must be equal to either x or z. Right? This is on the sphere, you know that if you take any, you don't have solutions to this equation with x, y, z all lying on the boundary of the sphere. Okay, there, if you take the line joining these two, it cannot contain, the midpoint cannot lie on the sphere, as is geometrically obvious, and you will prove it in a moment if you wish to do. So the midpoint of this cannot be on the sphere. So you can't have a solution to this equation with x, y, z all lying on the sphere. So Behrend's idea was to take integer coordinate points on a sphere and project that set to the line. You just project that set to the line and make sure, project meaning as in map it to the line using a particular linear map, and then making sure that that linear map is injective, so it takes all these points to a set of the same cardinality and moreover has this property that there are no, it preserves, I mean, the function has the property that if there is a 3-term AP here, then there should be a 3-term AP within the set, the domain, but then since there are no 3-term APs in the domain, there won't be any in the image set. So the image set will be free of 3-term APs, and you know the cardinality of that set, and by estimating the cardinality of the set relative to the size of the interval in which it lies, you get the theorem of Behrend. Okay, so let me just explain the details for those who have not seen it, because this is an important example in this subject. It's the only sort of lower bound that is known. So, yeah, you project to the real line. No, not project, that's what I said. I mean, you map it to the real line. I'll give you a function whose image, I mean, the image of this set of integer points under that function will give you the set that you will, that will not contain 3-term APs. Okay, it's a linear map, okay, but it's not a projection. So first, what should one do? You consider, I'll let m be greater than equal to 1 and n greater than equal to 1. These two numbers will be fixed at the end, okay, depending on our requirements. So let m and n be two integers greater than or equal to 1. And now consider the points belonging to, let x belong to 1 m to the power of n, x equal x1, x2, xn, each xi an integer. So consider the integer points belonging to this n dimensional set, this cube in the integers. Okay, so now look at the norm of the square of the norm, which is x1 square plus x2 square to xn square. Consider this, which satisfies norm x square is less than or equal to n times m square and greater than or equal to n, right? Because each entry here is greater than or equal to 1 and it's less than or equal to m. Each xi is between 1 and m. So this sum of squares is going to be between n and nm square. Okay, so now if you look at the map from this set, so let us consider this set as, so from, and the map, thus the map x going to norm x square has maps set 1 or maps the set 1m with m to the power of n elements to a set with n m square minus n plus 1 elements. Okay, so it maps this many elements to a set with this many elements. So pigeonhole principle says that the cardinality of the fiber of this map for some value must be at least. Therefore, there is at least there is by pigeonhole by whatever pigeonhole principle abbreviated appropriately, okay, there is an r integer, there is an integer r such that at least m to the n divided by n m square minus n plus 1 of n m square, this many x's, okay, this at least this many integer points means x element 1 m to n satisfy x1 square plus x2 square xn square equal r. Right? Yes, pigeonhole will tell you that this norm, at least this many elements have to be there above some r. Okay? So this means from this we get okay, so this means, so let S be this set. So there is such that at least this many integer points satisfy this. So let S be the set of such integer points. So what I mean by this slightly vague statement is that cardinality of S is greater than m to the n by n m squared minus n plus 1, which is greater than m to the n by n m squared, which is greater than m to the power of n minus 2 by n. Right? So cardinality, that is cardinality of S is bigger than m to the power of n minus 2 by n. So this is one thing that you'll remember. Okay? Yep. Any mistake? Pardon? N. No, that's not an M. That's just poor handwriting. That's N. Okay? So first of all, this is true. And secondly, and also, if x1 square plus x2 square plus xr square, xn square equal r for each x equal x1, x2, xn in S, and each xi is in 1 to m. just to overemphasize this fact. Okay, so you have a set of at least this many elements, what shall I say, entuples, which all lie on a sphere. Okay, the main property is that they all lie on the same sphere, and they all are integer points, and we have shown that there exists a large number of integer points on some particular sphere, okay, with coordinates all between 1 and m, and this follows from pigeonhole. Of course, pigeonhole will tell you that there is an R, but it will not tell you the arithmetic nature of R, which is of course a hard question, but that is irrelevant to our theory. Okay, so now coming to, and that's basically the first idea, to produce a sphere with large number of integer points. Okay, that's just done by a random, meaning pigeonhole argument. And now you consider a map which will map these integer points onto the real line. Okay, now this is the second part of the argument. Consider the map here. X goes to the sum of 1 less than I less than n, xi 2 to the power of m I minus 1. Okay, so what this is doing is sending the point with coordinates x1, x2, xn to the integer written in base 2m, okay, with those digits. The meaning of this map is that you take a point, let us say 1, 2, 5, 7, 11, and send it to the point which has digits 1, 2, 5, 7, 11 in base 2m. Okay, that's precisely what this is. It sends this to that. This map is used in a number of places when you want to separate, when you want to keep things injective. Okay, so this is a very nice injective map, because you know the as long as the xi's don't exceed 2m, which is the case, even xi to minus, and even the difference between them, maximum goes up to m to minus m. So this representation will be unique, okay, and that's really the point that's being used. This is used in a number of situations. I'm sure, for example, like in Fourier series, in commutative algebra, like Noether normalization theorem uses a similar trick. This is there in many places, so it's not. Okay, so now you consider this map. Now what sort of a map is this? So if you consider this from S to, this goes from S to Z, really. In fact, it goes into the natural numbers. If you consider this as a map from S to Z, F is the restriction of R linear map. Okay, this map is actually on Rn, it's an R linear map. You just take any point and send it to this thing. It's obviously R linear. Okay, so F is the restriction of an R linear map. Okay, also we have the main point here that if f of x is so also for x in minus 2m to 2m, f of x is 0 is equivalent to x is 0. There is only one 0 in this interval. Okay, so minus 2m to the power n. So if all the coordinates lie in this open interval, then f of x is 0 means that x is 0. Simply because f of x being 0 means what? it means that the sum of this sum is 0. Now, suppose this sum is 0 and you want to show that in fact all the xi's must be 0 provided they satisfy this size condition. Okay? Let's assume that x2 is the first non-zero xi. So then what will you get from this relation? You will get that x2 times 2 to the 2m is equal, if I take the rest to the other side, x3 onwards. So xi 2 to the m I minus 1 for I equal 3 to n, right? And I can cancel the 2m and I'll see that this side is a multiple of 2m, whereas this side, therefore this side must be a multiple of 2m and must lie in the open interval minus 2m to 2m, which means it has to be 0. So it's just as elementary as that, simply modular arithmetic. It has to be, it's just representation in base 2m, there's nothing else. Okay, so this condition here, I mean this fact now implies that f satisfies the following property. This means, this implies that for any x, y, z in S, the set we looked at, x plus y by 2 equal 2z is equivalent to f of x plus f of y equal to f of z. This is equivalent. Okay? Now why is it equivalent? Because f is R linear, so this can be, this condition would mean, of course if this is true, and the only thing, because f is R linear, and if this is true, again because f is R linear, this reduces to x plus y minus 2z equals 0, and then use the fact that x plus y minus 2z is x minus z plus y minus z, and x, y and z belong to S, and S contains only points whose coordinates are in 1 to m. So x minus y lies between minus m to m, and x minus y plus y minus z lies between minus 2m and 2m, which is exactly the open interval we spoke of here, and therefore this being 0 would mean that x plus y minus 2z is 0, and that is this. So you see f has the property that if x plus y, it preserves APs. In the image, if there is an AP, there will be an AP, the inverse image will be a 3-term AP and conversely. Okay? Yes? Yeah, it preserves APs, meaning I want to actually conclude that f of S, the image of S, contains no 3-term APs. Okay? How will I do that? Because S consists of points all on a certain sphere, and therefore it doesn't, that S doesn't contain 3-term APs. Okay? And therefore f of S doesn't contain 3-term APs. Because if f of S had a 3-term AP, it would mean that S itself has a 3-term AP. Right? Therefore, f of S doesn't contain 3-term APs. So from this you conclude that since S does not contain 3-term APs, meaning does not contain a solution to x plus y equal 2z, it follows that since S does not contain a non-trivial solution to x plus y equal 2z, it follows that f of S also does not contain such a solution. That is, f of s has no non-trivial three-term APs. Okay, so this is the nub of the argument. You come up with a natural example which doesn't contain three-term APs, namely the boundary points on a sphere, which for obvious geometric reasons they are extreme points, they don't contain three-term APs, and then make a map which preserves the structure, that is x plus y equal 2z will be satisfied if and only if f of x plus f of y equals 2f of z. Okay, you take such a map, that map is injective on the set that you are considering, and its image doesn't contain any three-term APs, so you have constructed a set with no three-term APs. The rest of the argument is only to estimate the size of this set. There's nothing left. Once you've got this, you know a bound for the size of the set. We know that cardinality of S is greater than now cardinality of S is greater than m to the power of n minus 2 by n, which implies that cardinality of Fs is also greater than Fs is also greater than m to the power of n minus 2 by n. That is one thing, because F is injective for the same reason, and next thing is Fs has no three-term APs. All I have to now tell you is what is the interval in which Fs lies. So Fs lies in the interval 1 to 2m to the power of n. Because Fs, if you look at the definition of Fs, which I have erased conveniently, so if you look at the definition of Fs, it is simply the digit, the representation in. So the definition of Fs was f of x was xi 2 to the m I minus 1, 1 to I, n, and each xi lies between m and 1. So f of x lies between 1 and m times 2 to the m to the n minus 1 by 2 minus m minus 1, which is certainly less than 2m to the power of n. Okay, certainly less than 2m to the power of n. So you have produced a set for any integer m and an integer n, which has cardinality greater than equal to m to the power n minus 2 by n, okay, and has this size. Now you take your capital N to be 2m to the power of n, and you take your small n to be square root of logarithm of capital N, and you just plug in these things and you estimate the size. You will get here from the fact that m is actually n to the power of 1 by n by 2, you will get with this choice of n an exponential, say 4 times root log n or so, just by plugging in the values, and that proves Behrend's theorem. Okay, so it's a very simple thing once you know the proof. It's easy to remember. It's just project from the sphere, from a sphere which is known to have a large number of integer points to an interval using the digit map. Because all these are clever ideas, but they are actually quite natural in the context. Okay. Good. So we are done with this. Tomorrow I start to prove Roth's theorem. Right. So 2:30 after lunch.